Hello, I'm Toby Delbruck, and I'm going to be telling you about the PhD project work of Min Lu, which is Edflow, event-driven optical flow camera with hardware keypoint detection and adaptive block matching. We are with the Sensors Group at the Institute of Neuroinformatics, University of Zurich, and ETH Zurich.
So Edflow uses a DVS dynamic vision sensor event camera input. As shown in this figure, the events are moving in a 3D time space in response of different shapes. The dataset is from robotic perception group. So what we want to do is to extract corners to avoid aperture problem and then estimate optical flow on these corners, eventually in purpose of visual geometry, SLAM, or other applications.
The most closely related work is from the group of Garrick Orchard at NUS Singapore. It uses the local planes method to fit a local plane to the timestamp image at the location of each event. And you can see here a video from their paper that shows the flow output from the DVS input. It shows the direction and speed of the flow. And this is a nice implementation that cleverly avoids multiplications by using lookup tables to do the matrix operations. The problem with it, like these other previous implementations, is that the optical flow accuracy is rather poor. Here you can see the average endpoint error in pixels per second of these other methods previously published with our work. Our method is 8 times more accurate than theirs, and it's 5 times more accurate than the IBM True North method, which uses a lot of CPU computation to finally compute the optic flow.
Here is an overview of Edflow camera keypoint and optic flow computation. We started with an accumulated event slice, showing here a traffic scene. And then we find a corner here, which is on the edge of the traffic sign. If we magnify it, we get a histogram of these event counts. We detect corners by looking for a streak whose value is larger than all the places on the streak on the ring by some threshold amount. Once we find these corners, we can either computing optical flow on all events or only these corner events to mitigate the actual problem by using a block matching approach. It starts from the location of a new event and use a reference block which is centered on this event and in slice t-1 and a search area in slice t-2. Once we find the best matching target block in slice t-2 over this search area, the optic flow is obtained by the multi-scale displacement divided by the event slice time delta t, which is variable. It depends on our event slice exposure strategy. The output is a stream of optical vectors along with its original DVS events. And the feedback control of the slice exposure is to keep the average optical length in the center of the multi-scale search area range.
This video shows the Edflow camera hardware. The PCB, the command monitor, and the display monitor. Here is our Davis 346 chip mounted under a C-mount lens mount. There's the XC7100 Xilinx FPGA. It's a 6-layer PCB. And then there's a USB PHY that allows the output to be sent to the computer, where we can display it in response to live input. We can also control the camera modes for corner detection, optical flow, threshold. We can play back recorded stimuli to the camera or show it live, things like this checkerboard where the optical flow vectors are represented by colored arrows of different lengths.
As shown in the spinning dot Edflow example, the dot spins at 720 RPM and the dot speed is about 8,000 pixels per second. ABMF computing software is much slower than real-time, but it's faster than real-time on Edflow hardware. Here we slow down by 10x to show the flow vectors.
This video shows Edflow optical flow for an apartment scene outdoors and indoors. The main thing you should notice is that the optical flow vectors, as a result of the panning motion of the camera, are all about the same length and the same color. That's what you would get from panning motion. And the video shows that even under increasing scene complexity and especially increasing camera noise level, the optical flow is still computed even under this incredibly high noise situation where there's an immense amount of DVS shot noise.
So here we show an example of our Edflow camera computes realistic optic flow on the real scene from our DDD20 dataset. This scene is recorded on the way to the Zurich airport.
This example shows a driving video taken from YouTube where a child runs in front of the car, and we synthesized realistic DVS video using our V2E tool. Here you can see the child, and now Edflow computes the optical flow for this scene, the expanding optical flow, including the motion of the child in front of the car.
To conclude, the Edflow camera is the first device camera that finds key points and optic flow. Both of them are computed by logic in an integrated FPGA. Key points are first extracted by SFAST. Optic flow are then estimated only on this extracted key points by adaptive block matching optic flow. It can compute key points and optic flow with less than 1 millisecond latency and 1 watt of FPGA dynamic power. The paper includes Java source code for ABMOF and high-level synthesis source code for the entire Edflow pipeline. We would greatly acknowledge the support by Swiss National Center for Robotics.